Hello. In this video, we will be practicing deriving expressions for indicated variables. Practice for the AP Physics 1 exam. Remember to pause or rewind the video as necessary. In this video, we're going to be working on problem number 4. Let's begin. Remember to list any and all concepts before you actually attempt a problem. In this problem, we have two carts, one mass m, the other mass 2m, are compressed the same distance d against identical springs with spring constant k and released from rest. They separate from the springs and collide and stick together. Derive an expression for the speed they will be moving just before the collision in terms of m, d, k, and fundamental constants. One of the things I noticed right off the bat is that if both of them are spring loaded and launched, we have conservation of energy from cart 1, and we have conservation of energy from cart number 2. Now, when these carts meet in the middle, we're looking at conservation of momentum. Now, they collide and stick together, so we're looking at an inelastic collision when they do stick together. Those would be the two concepts that immediately come to mind when starting to take a look at question problem number 4. Now, you have to do conservation of energy for both of these carts, okay? So in both cases, conservation of energy, we have energy initial equals energy final. Well, the initial energy is going to be spring-loaded energy, as we saw in problem number 1, and that's going to be transformed into kinetic energy for each cart. The kinetic energy of each cart is going to be the same because the spring energy will be the same for each cart. The speed, however, of cart 2 should be less than the speed of cart 1 simply because it has more mass. Well, we can substitute for the actual equations for spring potential energy and kinetic energy, and we get 1/2 k. Normally, we would write 1/2 kx squared. However, we were told that the spring distance is d. So we're going to use that kd squared equals 1/2 mv squared. Now, remember with the other problems we've done to this point, the velocity is the concept that connects these concepts. So be prepared to solve for velocity in most instances. So we're going to do that. We're going to go ahead and I'm going to rewrite it real quickly. 1/2 kd squared equals 1/2 mv squared. We're going to multiply by 2, divide by mass, and then we'll end up square rooting. So the v is equal to the square root of k times d squared over the mass. Okay, now that would be cart 1. So this is conservation of energy. This is specifically cart 1. Now, cart 2. Same idea. Spring potential energy equals kinetic energy. Same initial energy, 1/2 kd squared, because it's the same compression, same spring. However, and it's going to be the same total kinetic energy. However, the individual speed of cart 2 will be different. And that's because it has twice the mass. Therefore, it's going to have less speed. Now solve for that speed, and we get v is equal to, when the halves clear out, the square root of kd squared over 2m instead of m. So we've got a speed for cart 1, which I'm going to call v1. We're going to have a speed for cart 2, which I'm going to call v2. Well, conservation of momentum is now our new concept, and that's where they meet and crash into each other right in the middle. And we have what's called an inelastic collision. Now, the equation would be momentum before the collision equals momentum after the collision. Now, before the collision, you have two objects moving, m1v1 plus m2v2 equals, and then when they collide, they stick together. So that would be m1 plus m2 times v final. Now, we need to establish a reference frame. I'm going to suggest that cart 1 going to the right would be positive velocity and positive momentum, therefore, and cart 2 going to the left is going to be negative velocity and therefore negative momentum. So this would change to, and we're going to actually substitute variables now, m times v1, the expression for v1 is right here, substitute, m times the square root of k d squared over m minus, because we have negative momentum here, minus 2m times the square root of k d squared over 2m. So in place of v2, I substituted the expression for v2. Well, that's going to be equal to, now the final momentum is going to be m1 plus m2 would be m plus 2m, which is 3m times your v file. And that's ultimately what we are looking for right now. So let's go ahead and divide away the 3m to all parts. Notice the masses cancel, and you have an expression for the final velocity after collision. So 1/3 times the square root of k d squared over the mass minus 2/3 times the square root of k d squared over 2m. And yes, you could pull out a d on this right here, and yes, you could clean it up, and yes, you could simplify this expression, but honestly, you don't get any extra points for doing so. And if the instructions did not tell you to derive and simplify, then you don't. Expression, derive an expression in terms of m, okay, dk, okay, and fundamental constants. Now that would be g, but g is not a part of this one, so that is a sufficient enough solution. Are the carts moving left or right after collision? Well, cart one is moving. Let's see what's going on here. Cart 1 is moving with speed and with momentum mv going that way. Cart 2 is moving with momentum mv going that way. Now, the mass might be double, the speed might be less, but it turns out because it is the square root of half your mass, or you're taking the square root of that reduced doubled mass. So then what would you end up with is you end up with a little bit less, you get a little bit less velocity, but it turns out that the doubled mass is actually more than the less velocity. So you actually have a greater momentum coming from the left than you do the right. So the total momentum of the system is, before collision, directed left. The total momentum is left before the collision. And this again is because cart 2 just has an overall greater momentum before collision. Okay, now since momentum is conserved, the momentum will be left after collision. If mass were decreased, would the final speeds increase, decrease, or stay the same? Well, you'll notice mass is in the denominator of the expression. So since mass is in the denominator, of the expression, a decrease in mass would result in an increase in the final speed after collision. No, this is a typo here. If mass d were doubled to 2d, no, it's distance. Distance, little typo there. If distance d were doubled, by what factor would the cars change? We'll look at the expressions here. Look at the expressions. You could pull out a distance for each one. Remember, you could rewrite this equation, this expression rather. In fact, I'll rewrite it down here. So v final would be 1/3. I could pop out a distance there because the square root of d squared is d. So 1/3 d times the square root of k over m minus 2/3 d times the square root of k over 2m. And you can see, if I factor out a d, what that really means is the final velocity is directly proportional to d, because nothing else would change. So if the distance is doubled, if d is doubled, then v is doubled. Good practice with proportional reasoning on this one. If the springs were replaced with 1/4 the spring constant, by what factor would the final speed of the carts change? Well, you can see that if nothing else changes, v would be proportional to the square root of k, which means v final would be proportional to the square root of 1/4, which is 1/2. That means reducing k by 1/4 reduces the speed by half.